Hey guys, welcome to another session on math for data sciences. So before moving on to more properties of exponential distribution, which we looked in our previous session, we wanted to discuss some of the major properties of logs. So what are logs? So we first need to understand what exactly log represents. So for example, if we are given log b to the base a equal to x, what does it mean? So the first thing here is log b to the base a. So this is how we write this is the definition of this particular notation, log b to the base a. This is how we write it. Now what this means is, this means b is equal to a to the power x. So whenever we have this kind of a relationship between three numbers b, a and x, we can write this relationship as log b to the base a is equal to x. Now we'll be looking at some properties of logs, which we'll be using in general for various metrics definitions. So first property is product rule. This we have seen before as well. So what product rule states is log of xy to some base a is nothing but log of x to the base a plus log of y to the base a. So the base remains the same, and instead of product we can separate out two different logs and we just need to add them. So this is the product rule. Next we have a quotient rule, and this states that log of x upon y to the base a is nothing but log of x to the base a minus log of y to the base a. So instead of adding here, we are subtracting. That is the only difference between the product rule and the quotient rule. Next, we have something called a power rule. Again, we have seen application of power rule before in our previous sessions. I'll just mention it here. So log x to the base r, log x to the power r to the base a is given as r log x to the base a. So we simply can take the power in front of log here. This is the power rule of logs. Now next we have logarithmic of 1. So log of 1 to the base any base a is always equal to 0. Why is this? Because a to the power 0 is always 1. Therefore log a to the power 0 is equal to log of 1. If we take log both sides, and a to the power 0, we can bring 0 here, 0, and therefore log 1 becomes equal to 0. So this is the property that log of 1 of to the base any base is always equal to 0. Then we had log of the base. So log of the base means we are keeping the log and the base the same, and this is always equal to 1 because a to the power 1 is a. So we can bring the power of a to as 1 to get an a itself. Now next is change of base property. So again, this also we have seen before actually. So what happens is, let us say we have a log, and we have log x to the base a. Now let us say we want to bring it to a different base, and let us say we want to bring it to base b. So what we do, we simply write it as log x to the base b divided by log a to the base b. So what this means is that to bring it in the same in a particular base like b in this case, we need to keep the base for both x and a the same, and we simply divide by log a to the base b, where a was the previous base to the initial log. So this is called the change of base property. Next we have inverse property. So here what we have is a to the power log of x to the base a is equal to x. Now this can actually be derived as well. So for example, if we take, let's say we have a to the power log x to the base a, and now let us say we take log of this. So let us say we have a here. Now if you guys remember from the initial definition, if we have a relationship b equal to a to the power x, we can write it as log b to the base a equal to x. So in this case the power is log x to the power a itself, so we can write it as log x to the base a equal to log x to the base a, because this a, basically this a is this a, and this log x to the base a is this particular term. So we simply use the basic definition of log to verify this relationship. Next we have reciprocal identity. So one does not need to really remember the name of the properties, but only how the properties could be used to derive various metrics. So log x to the base a is nothing but 1 upon log a to the base x. This is because we can use the change in base property. So if you remember, this can be written as log x to the base b upon log a to the base b by using change in base property. Now this is nothing but log a to the base b upon log x to the base b whole raised to power minus 1, and this is log a to the power x raised to power minus 1, which is 1 upon log a raised to power x. So we use the change in base property to get the reciprocal identity. So majorly the first three properties are the more important ones here, which would be used again and again, but just for the sake of completeness, we have all these properties of log that would be often used in various applications. Now this is about logs, so we'll be moving back to what we studied in the previous session about exponential distributions. So if you remember, we looked at the CDF of exponential distribution, which was derived using the PDF of the Poisson distribution, and it was given as fx equal to 1 minus e to the power minus lambda x, and then we had differentiated this to get the PDF of the same distribution as e to the power minus lambda x, and both these definitions are defined for x greater than 0. This was the range of an exponential distribution. Now once we had gotten this PDF, what we did was we calculated the expected value as 1 upon lambda, then we calculated the second moment of x, which was 2 upon lambda square, and using these two, now we got the variance as 1 upon lambda square. So the variance is nothing but square of the mean for an exponential distribution. Then we had also obtained the quantile function, using which we had obtained various quantiles, including the median, the first and the third quartile, and the interquartile range as well. So interquartile range came out to be ln 3 upon lambda. So this is ln 3 upon lambda. Now once we have seen these metrics, we'll be looking at a new concept here, which is called outlier detection using Tukey criteria. So whatever concepts we are looking at here for exponential distribution, we can actually calculate all these different metrics which I'm calculating for other distributions as well, but we are just using the exponential distribution to introduce and explain these new concepts which we have. Now according to Tukey criteria, we declare a point an outlier. So an x value is an outlier. By outlier I mean unusual values which are normally not expected from a distribution, or the probability of those values occurring is very, very low. So the nx value is an outlier if x is less than q1 minus 1.5 times IQR, or x is greater than q3 plus 1.5 times IQR. So what we mean here is, if so, let us say we draw a number line here. This basically contains all the possible values of x. Now we know that the middle value m is the median, which was calculated for exponential distribution as ln 2 upon lambda. Then there must be a third quartile value, which was calculated as ln 4 upon lambda. And then we also had a 25th percentile value, which is the first quartile value, and that was calculated as ln 4 upon 3 upon lambda. So these were the three values which we had derived, and we also saw that the difference between q1 and q3, that was the interquartile range, was given as ln 3 upon lambda. So these were the various values which we had defined in our previous session. Now to calculate an outlier, now note that there are still 25% of values which are less than the first quartile of the distribution, and then there are 25% of the values which are more than the third quartile of the distribution. So we can extend this number line to represent some of the values. Now it is possible that let us say we have certain points here. So we have these points represents various x values, but then there is always another range of values. So let us say we make a new range here, this particular. Now for this range, what we say, these are an outlier from the lower side, and this gives an outlier from the higher side. So not all the values less than q1 are outliers, but a distance from q1, if we go towards the left side and we make a particular, let's say we use this Tukey criteria. So this particular value is calculated as q1 minus 1.5 IQR, and what we say is all the values which are less than this particular values are outliers or unusual values on the left side. So for exponential distribution, this can be calculated as ln 4 by 3 upon lambda minus 1.5 ln 3 upon lambda. So this is the left hand limit for an exponential distribution, and any value which is less than this particular value will be an outlier. Similarly, for the right hand side limit, we have x greater than ln 4 upon lambda plus 1.5 ln 3 upon lambda. So all the values which are greater than this particular x value for the exponential distribution will be an outlier on the right side of the distribution. So this is what the Tukey criteria says, that any values which are less than 1.5 IQR times the first quartile value, those values are equal to outliers on the left side, and similarly we have the criteria on the right side for the outliers. So this is the criteria which one needs to remember. So this is about the Tukey criteria. Next we would be looking at something called a memoryless property of an exponential distribution. So let us say we have the CDF of the distribution right now as fx equal to 1 minus e to the power minus lambda x. Now by definition, the CDF represents the probability of the random variable taking a value less than equal to x, and therefore this is minus lambda x. Now using the complement rule of probability, we know that x greater than x should be equal to 1 minus e to the power minus lambda x. This is because p x less than equal to x plus p x greater than x has to be 1, because these are the only two possibilities that can happen. Therefore p x greater than x is 1 minus p x less than equal to x. Now we can cancel out 1 and 1 here, and we would be left with p x greater than x is equal to e to the power minus lambda x. So the probability that the waiting time is more than this particular small x value is given as e to the power minus lambda x for an exponential distribution. Now let us say we come to a bus stop. So there is a bus stop where rate of bus arrivals is lambda. Therefore waiting time for bus could be modeled as an exponential distribution with the rate parameter as lambda. Now let us say a person comes at 8 a.m. to the bus stop, and it is already 8:10 a.m. There is no bus yet. And now let us say we have to find the probability of no bus for another x minutes, given that there is no bus from last 10 minutes. Because we already know that there has been no arrival from 8 a.m. to 8:10 a.m. Therefore, we are already given this condition here that there is no arrival in the last 10 minutes. We have to find the probability that there will be no bus in the next x minutes as well. So what we do, we have to calculate p x greater than equal to 10 plus x, given that x is greater than 10. So the condition here, this is the given condition, which is that the waiting time is already more than 10, and we have to wait another x minutes. Therefore the total waiting time we want is 10 plus x. Now if you guys remember from our sessions on probability, we had studied something called a Bayes theorem for conditional probability. What this theorem suggested was, for any two events A and B, the probability of A happening given that B has already occurred was given as probability of A intersection B. So by intersection we mean that both A and B have to occur, divided by the probability of B happening. So in this case it would mean, now applying in our particular scenario, this would mean p x greater equal to 10 plus x and x greater than 10 and divided by p x greater than 10, because x greater than 10, this is the given condition. So let us look at it in more detail. In fact, now we are already given a condition here that x is greater than 10. So this is the condition given to us, and we have to find the probability of x being greater than x plus 10. So probability required, we'll just mention the Bayes theorem here as A and B, which was given as intersection operator, and divided by PV. So if you guys see carefully, this is actually the condition which is B, and this is the event A. Therefore we can write the numerator now as Px greater than x plus 10 and x is greater than 10 divided by Px greater than 10. Now, since if x is greater than 10 and if x is greater than x plus 10, if we have to find the intersection of these two events, it would simply mean x is greater than x plus 10, because if x is greater than x plus 10, then it has to be greater than 10 as well. Therefore, if we want both the events to happen, we can just let this particular event happen and the other one will automatically happen. So if x is greater than x plus 10, then x has to be greater than 10. Therefore, this could be written as Px greater than x plus 10 upon Px greater than 10. Now, since we have already seen for exponential distribution, that is x, so we already saw Px greater than x was e to the power minus lambda x. So this is what we just saw here when we were looking at, when we use the complement rule. So here we had got this relationship Px greater than x is e to the power minus lambda x. So we can simply use this particular rule in this condition and we get e to the power minus lambda x plus 10 divided by e to the power minus 10 lambda, because we have in denominator we have x greater than 10, therefore it becomes e to the power minus 10 lambda, and in numerator we have x greater than x plus 10, therefore it becomes e to the power minus lambda x minus 10 lambda. Now this can be written as e to the power minus lambda x plus 10 minus 10, because we can basically add subtract the powers of e from numerator to denominator, since this is in denominator, and therefore we will be left with e to the power minus lambda x, which is same as Px greater than x. Therefore, what we can conclude here is Px greater than x plus 10, given that x is greater than 10, is nothing but Px greater than x. Now what does this mean based on our given problem statement? This means the probability of waiting for another x minutes given that 10 minutes have already passed still remains the same. So this is like saying if we would have come at 8 AM, then also the probability was e to the power minus lambda x, and now at 8:10 AM, if we are calculating the same probability that we have to wait another x minutes, it still remains the same. So that is also why this is called the memoryless property of an exponential distribution, because it does not care how many minutes have already passed, and the probability distribution of the waiting time still remains the same. So the probability, since the probability distribution remains the same, we can also write this as x, given that x is greater than 10, is still exponential lambda. So the distribution of the waiting time x, given that x is greater than 10, still is the same distribution, which is exponential distribution, and with the same parameter value lambda. So this is how we can derive the memoryless property of an exponential distribution. Okay, so moving on, we would be looking at, so we have been looking at these nth moment calculations. If you remember, in all these continuous distributions, we calculated the mean as Ex, and in case of exponential distribution, where the parameter is lambda, we calculate this as 1 upon lambda. Then we also calculated the second moment of x, which was 1 by lambda square. So these ex to the power n, this is also called the nth moment of a distribution. So just wanted to mention it here for the sake of completeness. This is also called the nth moment of a distribution, what we have been using till now to calculate the mean and variances of the various distribution. Then there is another term. It is called the central moment. So nth central moment of the distribution. Now, what does a central moment means? Instead of calculating the nth power of x expected value, what we calculate here is we calculate the expected value of x minus mu raised to power n, where this is the mean of the distribution. So for example, in this case, if we have to calculate the first central moment, that would be E x minus mu. Now since this is a linear combination, we can separate the expected value terms to get E x minus E mu. Now since mu is a constant, it is a mean value, this can be written as mu because expected value of a constant is same constant. Also the expected value of x is nothing but mu, therefore this is 0. So one has to remember that first central moment of every distribution is 0. So this is regarding the central moment. Now we can also look at an example where we are trying to calculate the second central moment of the distribution. So let us say we want to calculate the second central moment, which is calculated as the expected value of x minus mu whole square. Now this can be written as expected value of x square plus mu square minus 2x mu. This is because we use the algebraic identity here, which states that a minus b whole square is a square plus b square minus 2ab. So we use this identity to get to this expression. Now once again, expectation of linear basically linear combination of different operators, we can separate the expected values and we get expected value of x square plus expected value of mu square minus expected value of 2 mu x. Now since mu square is a constant, we can write the expected value as it is. Expected value of x square we can keep right now it as it is, minus, now 2 mu is constant, so we can bring that out and we have expected value of x. Now for exponential distribution, we already know expected value of x was 1 upon lambda and expected value of x square, like we calculated in our previous session, it was 2 upon lambda square. Now putting these values, we get 2 upon lambda square plus 1 upon lambda square because mu is 1 upon lambda minus 2 upon lambda into 1 upon lambda. And 2 upon lambda square and 2 upon lambda square cancels out here and we are left with 1 upon lambda square as the required value. So this is how we calculate the nth moments and nth central moments of any distribution. The only difference between nth moment and nth central moment is we calculate the central moments about the mean of the distribution. So in this session, we first looked at some log properties and based on which we use the Tukey criteria for outlier detection. In there, what we saw was any value of the distribution that is less than Q1 minus 1.5 times the IQR, which is the interquartile range, is considered an outlier value from the left side, while those values which are greater than Q3 plus 1.5 times the IQR value are considered outliers on the right side. And after this Tukey criteria, we looked at the memoryless property of exponential distribution, where we saw that the probability of waiting another x minutes, given that some time has already passed, still remains the same, and the distribution of waiting time also remains the same irrespective of how much time has already passed. After that, we looked at the difference between nth movements and nth central movements of the distribution, and we derived the first and the second central movement for an exponential distribution. So we saw that first central movement for every distribution is 0, while we were able to get the second central movement of the exponential distribution as 1 upon lambda square. So this is it from this particular session. We'll be using this nth central movement theory in the next session, when we are looking at some higher movements of the distribution which are relevant for an exponential distribution and many other distributions in general.